Today in Capechi's Corner, we're going to look at segments, rays, and distance. In looking at the different figures in geometry, we have to make sure we are okay with the notations. So the first one we're going to look at is segment LM. So I put a segment bar on top. I know that I'm talking about this figure right here, L and M. They're each endpoint, so they're talking about segments. I could also name that one segment ML, and I would just write that like that. And looking at the next example, I'm talking about a ray LM. So with that, ray LM, I'm starting at the endpoint L, and I'm continuing in the direction of M. So it is important which one I write first. When we're looking at opposite rays, we're talking about rays that must start at the same endpoint. So if I'm talking about ray AB, it starts here at A, that's my endpoint, and continues in the direction that's going to pass through B. Or I'm talking about ray AC, again, that's an opposite ray because they both have the same endpoint. They're starting in the same spot, but continuing in opposite directions. And looking at the examples below, these are not opposite rays. So we have to discuss why that they are not and make sure we're understanding the diagrams. So in the first example, we have ray AB, which would continue on that direction, and ray BC, which would start at B and continue in that direction. They are not opposite rays, not only because they don't share the same endpoint, but because they both are continuing in the same direction, so inevitably you're talking about the same ray, the same direction. One is just starting at A, and the other one is starting at B. When I'm looking at the next example, I have ray BA, which starts at B and continues to A, and then I have ray CD. And this one sometimes confuses students because although they are going in opposite directions, they do not share the same endpoint, so they are not considered opposite rays. Now we're going to talk about the segment addition postulate. This is a big postulate that we use a lot in geometry. It states that if B is between A and C on the same line, then AB plus BC is equal to AC. So basically, two small segments equal the bigger segment. Now notice when we're using the segment addition postulate, because there's an equal sign, there is no segment bar above any of those segments. So AB or BC or AC, because we're talking about the actual measurement or the length of those segments, we do not include the segment bar on top. Now here's some use that I can use of that postulate. So if AB is equal to X, and I'm always going to label my diagram, if AB is equal to X and BC is equal to 2X plus 7, and I know the whole thing is equal to 34, I can set up an algebraic equation. So I have X plus 2X plus 7 is equal to 34. Now again, two small pieces, two small segments equal my big piece. So now I just solve it algebraically. So I have 3X plus 7 is equal to 34. Bring the 7 to the other side, and I have 3X is equal to 27, so X is equal to 9. So that gives me a value of X. If I want to go back and figure out the length of these segments, to double check myself, segment AB is equal to X, so that would be 9. Segment BC is 2X plus 7, so that'd be 2 times 9, which is 18, plus 7 gives me 25. And when I add those together, I get 34, which is what we were talking about down here, that the length of AC is equal to 34. When I'm looking at some different vocabulary words, first I have the word congruent. They are any two objects within the same size and same shape. For example, your geometry books, if you're comparing your geometry book to the person sitting next to you, those geometry books have the same size and the same shape. You wouldn't necessarily compare your geometry book to a social studies book because that social studies book may be a different size, could be bigger, could be smaller, so they wouldn't necessarily be congruent. When I'm talking about congruent segments, they are segments that have equal lengths. So if I want to first talk about segments that are congruent, the symbols I use, there's segment AB with the segment bar on top. That's the congruent symbol. So that says segment AB is congruent to segment CD. If I want to indicate that these were equal, these segments are equal, I would say AB is equal to CD. Segment AB is equal to CD. Just remember that I do not use the segment bar when I have an equality, but I do use the segment bar when I'm talking about congruence. In looking at the midpoint of a segment, that's a point that divides the segment into two congruent segments. So for instance, if I have the segment AC and B is in the center there, I could say that if AB is 7 and BC is 7 as well, there's two things I can say. I can say segment AB is equal to segment BC, the lengths are equal, or I can say segment AB is congruent to segment BC. Now remember, when you're talking about the midpoint of a figure, you have to be able to measure it. So there has to be a start point and an end point. So a segment does that. A segment has a start, so in this case our start point is A and our end point is C. I can measure it so I can find the midpoint. When looking at other figures, I have to ask myself the same question: is there an end point on one side and an end point on another side? A line, I can't find a midpoint because a line goes on forever in either direction. So I can't measure it, so therefore I can't find a midpoint. The same thing with array. Array has one endpoint, but it goes on forever in the other direction, so therefore I can't measure it, so therefore it does not have a midpoint. Same thing with the plane. A plane goes on in every direction infinitely, so I'm not able to measure it, so therefore I am not able to find a midpoint. The last phrase we're going to look at today is a bisector of a segment. A bisector of a segment is a segment line, ray, or plane that intersects the segment at its midpoint. So again, I can only measure a segment so it has a midpoint, but I can bisect it with a number of different figures. In the first example, I am showing that a segment is bisecting another segment. And just remember that these little markings mean that those are congruent or equal. In the second example, again, I have a segment and I have it bisected, but this time it's bisected with a line meeting at its midpoint. In the third example, again, I'm bisecting a segment, but this time I used ray to do that. And then in the last example, number 4, I have a plane, and I can call that anything. I'll call that plane Y. And in this plane, there's a segment that has a length of 16, and I bisected that segment with a plane in this case.